So we're going to begin. So Mark Davis is an entrepreneur and technologist in the field of semiconductors, communications, signal processing, and system design. He was founder of Semiconductor via Telecom and of the ACGA. And today is the president of Crossbar, who has been working for a number of years on ReRAM memory. And Cramium is a new subsidiary of Crossbar who has presented before about their plans for a new secure processor. Mark, do you want to go ahead and take over the screen?
Sure. Oops. Okay. Okay. There. Is that working?
Yes, it is.
Okay, I have to start with a safe harbor. I will not read this word for word, but we touch on legal topics, so I will attempt to not say anything about them. So the outline is a little bit of background on what property rights actually apply to chips. And then I think a lot of people are kind of system software, so I think it's worth spending a little time on why ASIC is different from software. A really quick tutorial and copy left. Again, software people know this very well. Hardware people tend not to. And then practical consideration. Does open source hardware really achieve the same purposes as open source software? A quick review of some efforts to create open source licenses that are specific to the field of hardware. And then we'll talk about what we're doing with our chip. Yeah, unfortunately, we have to start with some very fundamentals. You might suppose that this kind of thing is obvious and settled. I just want to bring up that there is controversy. Copyright starts with some fairly simple act in 1790. Of course, with technology, the world got much more complicated. So then there's guidelines on what is copyrightable, what is not copyrightable. A great summary I would refer to reference number 1 in the references. Talking about guidelines, typically something that's purely utilitarian is more subject for patent than copyright, for example. The expression of an idea is copyrightable, not the idea itself. And then merger or sine faire are, if there's very limited room for expression, then that affects the copyrightability and so on. There's an excellent discussion with some case law in that article. So those of you who are as old as I am might recall that there was a time when people questioned, can software be copyrighted? If you go back and look at kind of first principles here, you could deduce that it's not sort of a priori obvious. And in fact, a seminal case was Apple versus Franklin, 1983. I think important point is this didn't go easily, meaning the district court actually ruled the opposite, that it was not copyrightable, and only reversed by appellate court. And ever since we've been following this, especially the executable form. If you look at executable form, does it really meet these tests? This was something that the district court opined that it did not. So the point is not necessarily obvious from first principles. We tend to forget that today because this was 40 years ago. So then does this apply to hardware? Does it apply to chips? Again, I'm not going to give my opinion. I would just point you to some references that discuss this. As pointed out in these references, I will elaborate on. A chip design involves diverse design artifacts, which if you were to compare them to these first principles, they compare in varying ways. So in the end, there's much debate about what type of intellectual property right even applies to hardware at all. There's some great analogies to software in some of the papers, but of course, these are papers, not case law. I will mention a couple case law items. This is by no means exhaustive list, but just to say, for example, one case holds a schematic is copyrightable, but a schematic, as we'll get into, is only one of many types of design artifacts within an ASIC development. Also, one thing that bears mentioning is there was a specific act in 1984 called the SCPA. A lot of people misunderstand this. It is not a copyright. It is not a patent, nor trademark, nor trade secret. it's a sui generis right. It means it's of its own kind. It's a mask work. That's what it is. For example, unlike a copyright, it has to be registered. So, this again is only one design of artifact in a chip, and it has its own one-off right. It's a mask work. I'd also point out reference 24 makes it clear that a lot of people don't register this. So, it's not used all the time. So where does that leave us? What intellectual property rights apply to hardware? It's a long story. I include this quote, not because I necessarily agree that the situation is this dire, but it's a succinct quote. This fellow says, it's unclear what we're licensing and therefore pointless to discuss the finer points of licensing. The other references would not depict it as such a dire situation. But the point is, there's a lot of controversy. It's less settled than you might imagine at first glance, and point to these references. So having discussed the futility of further detail, let's dive into further detail. I thought I would explain, just especially for non-ASIC people, how an ASIC is put together, in particular, why the IP concerns might be completely different from software, particularly when you talk about copyleft and the boundary of these things. So parts of a chip, not all of it, start with what looks like a programming language. Here's an example over here. You could read that, human readable. You could say that's very like software, right? So then the next step, and again, this is just the digital part, the kind of logic part, is to take that logical description, and then you get into something that starts to have a relationship to the factory. This is kind of descriptions of gates and so on. It might have setup, hold time, drive strength, things like this. And you map this into that and create a list, a sea of gates called a net list. Some authors make analogy of you're compiling software into an instruction set. One thing to point out, the use of the word library, completely different meaning than in software. So that's kind of the next step. These do have proprietary information of the factory that you're going to be making this at. The next step includes even more proprietary information. You take these kind of, this net list is kind of a logical thing, but then you map it into kind of a physical mapping of those gates in that process. And again, all of this, the size of those, the resistance, capacitance, inductance, what is manufacturable, what is not, that's all key information, not only from the foundry, but typically these would involve the foundry engaging a third-party vendor. You might not see it directly and have a contractual relationship with them because it passes through the foundry, but typically they will have engaged third parties in that. So here's another IP holder. That's just the logic part. And there's a lot more to a chip than that. There's memories. Of course, memories could be described as logic, but if you do it that way, they're very inefficient. So they end up being compiled in by a special tool that makes them much more efficient. There's things like IOs, ESD structures. There's very commonly you pull in many other third-party IP, phase lock loop, analog signals, power regulators. Maybe you have a processor core, some non-volatile memory or fuse for calibration. We talk about TR&G a lot. Even just kind of vanilla things like USB, that's complicated. You don't just connect a logic gate directly to the pin of the chip. There has to be a physical driver there and so on. And then there may be other specialized logic functions. These can come in various ways, which this affects what is complete source, what is allows you to use the design. They may come in as RTL, as we described. They may be just hard layouts that kind of get plugged in by the fabless company. In some cases, the fabless company doesn't even have access to them, and they would be plugged into the final layout by the foundry. And there's even more. We can go on and on. There's timing checks involves these laborious scripts. Development of scripts for timing. Well, it's kind of hard to use the code if you don't have this. This could go to the completeness of source. Test benches too. In software, you can incorporate software just compile it, see if it works, and so on. In chips, you cannot do that. The costs are extremely high. So for example, if I'm licensing something from somebody, I might ask, do you have test vectors that I can port to my test benches to make sure I've instantiated correctly? And I would say, if the vendor doesn't have those, I would find the block much less useful. And then we go to things for production tests. There are tools that insert, intellectual property into your netlist or into your final design. BIST, memory BIST. I didn't elaborate this acronym. This means memory BIST, memory built-in self-test for memories. Scan. Each unit has to be tested as you're making it. There's scan chain. These modify the design. Now, all of this is just digital. You also then would have analog, where you do a schematic. You use items from the physical design kit to help you design and lay out and verify that. There's a bunch of other quasi-manual tweaks to the layout, whereas software building takes minutes. If you go back and change one line of your RTL, you probably have 6 weeks to get back to the same point, et cetera. And all these things modify what you ultimately produce, which is a, GDS form is what ultimately creates the photographic plates that go to the factory. So the point of saying all this, I don't expect you to absorb all the detail, but just to say there are many stages. They involve varying third-party IP. And most importantly, those types are fundamentally dissimilar. In software, you have, essentially source, object, binary. And object and binary aren't that different. You typically would have like a linker locator that is resolving the addresses in the object file, but these two are kind of similar. There's not that many kinds of artifacts. We think of software as very hierarchical, but it's a conceptual hierarchy. In the end, it's all just code. Not so with chips. Real hierarchy, not a conceptual hierarchy of fundamentally dissimilar items. So this raises question of, for each of those items, is it what's the correct IP type, and what is the correct intellectual property right? What is source? And when we get into certain types of license, what is a complete or corresponding source? So this is to say that is much more complex than in software. A few minutes on copyleft. I think some of you know this very well, but some don't. It's a term that was coined to describe licenses that promote and require proliferation instead of prohibiting and restricting proliferation, like a copyright. Therefore, the play on words there. So typically you would receive, when you use inbound copyleft, you receive a license to use the code, but subject to certain obligations to publish and further sublicense what you've created. So key issues are, what is the boundary of that which you are obligated to provide an outbound license to? Licenses are described as permissive when they don't have copyleft, weakly reciprocal when they have, say, narrower rules for what's included in that copyleft boundary, or if they cast a wider net, then they're called strongly reciprocal. Looking at software licenses, really the 2 points here are, what do you have to work with in deciding what the rules are with copyleft? Well, you have a small amount of text in the licenses themselves. You have a huge corpus of literature, opinion, and de facto practice interpreting what copyleft means. And then you have a small body of case law. This reference gives not a complete summary, but a long list. I can't detail all this. There's entire careers just in the interpretation of copyleft. But the point I want to make here is that all of this, whether it's the text in the license, the case law, or the de facto practice and opinion, all of it is just chock full of terms like these. These are software terms: program, dynamically linked, statically linked, system library. I pulled down here, text directly out of GPL v3 and highlight in red things that, they have meaning in software, but how would you interpret this in hardware? It's like trying to take a rule from baseball and say, how would it apply to basketball? The question itself is almost nonsense, right? So even in a software world, where it's quasi clear what the individual terms mean, interpreting the relation is a field of active controversy. When the terms aren't obvious, then that just kind of exacerbates the problem. And why does it matter? I thought I'd give it just a quick picture of what it means when people say there's a license conflict. What is the problem? Well, if you take in a copyleft open source license and you take in a proprietary license and you combine them together, depending on what you do, the boundary of that open source license may expand, and it may then include the proprietary code. So in this derivative work, you have an obligation that you cannot license and cannot disclose, this obligation to the proprietary copyright holder. You may have an obligation that you must publish and must sublicense. To whom you have that obligation is, again, a field of controversy, but you have conflicting obligations. This can come up in software. And as previously noted, ASIC design is more complex with more contributors of more types of design artifacts. So avoiding this type of situation is more complex. I would say further, there are large companies that have a policy of, I will not allow any GPL v3 in the door because this is simply too complex in software. And if companies have that position in software, then you could question how would you, what should your position be in hardware, where it's even more complex to determine the ramifications. Also, there are real risks here. There are enforcement actions. Initially in the field of open source software, those were kind of institutional enforcement guided by ideology. More recently, in the last 5-6 years, there have been more activity in what people call, say, copyright troll, and so on. So the difference here, a couple. If it's copyright, note that has statutory damages. You don't have to show actual damages. And according to reference 1, goes into some detail pointing out that's really what gives open source its teeth, according to this reference. But of course, a big difference between software and hardware is a software provider might quickly and cheaply modify his code. ASIC vendor cannot do that, which then perhaps gives a troll more leverage. So there are real risks and consequences here. Moving on, I just briefly talk about, let's step back and say, open source hardware, what is the purpose of open source hardware? Why do we think it's desirable and so on? You can make analogy to software again. I pull up some of the 4 freedoms from the GNU.org website. But does open source hardware really provide these freedoms? Maybe for the sake of time, I won't go into detail here, but it's harder to say that it does because certain materials you can publish them, but they don't allow you to necessarily emulate precisely what will happen when you build silicon. Also, of course, actually building the silicon then is extremely expensive, and as we've already elaborated, involves a ton of third-party IP to get to a chip. So even if certain materials are open, the materials you need to manufacture it may not be, and so it's difficult. There are, I constantly hear about people who are maybe immersed in software saying, "Oh, I read an article about this open design flow. Does that really work?" Well, it has a place in the ecosystem. And I wouldn't want to say that that's not useful, but I think people tend to underestimate the vast difference between a low NRE design flow for prototyping and what you need to actually be in a semiconductor business. We all know that transistors have gotten, chips have gotten exponentially better in terms of cost, power, size, performance, et cetera. Well, that's been accompanied by an exponential rise in development costs. So these low NRE design flows are not the same. It's like, I make the analogy, I have a 3D printer that's consumer level sitting on the desk behind me. That doesn't mean I could be in the Lego brick business, right? That's a totally different thing in terms of manufacturing tolerances, volume, cost, et cetera, et cetera. So, electrons are free, atoms are expensive, right? Another big difference is inspectability. With code, because in the end you end up with a binary file, you can put a hash on it. Now you know that binary file hasn't been modified. With ASIC, there's just so many diverse levels of hierarchy. How do you know that what you get back matches what you think it is? Unit by unit, right? You just because one is inspected doesn't mean they're all the same. So there's things like signature, there's things like test vectors, there's things like optical scan. We'll go into that a little bit more, but each of those is a little bit limited. It's quite different from software. Also, there are different business considerations. So, for example, if I'm an outbound licensor of open source, I might think, well, community makes some improvements, I can rapidly incorporate those. With hardware, even if the community makes some improvement, it's not any easier for me to use them than it is for the community, right? Everybody has these cost barriers. So, lastly, I'll go through some licenses that are out there. If you go to a site like opencores.org, you can click on a bunch of tabs and see what kind of licenses. I would say by far the most common approach when people put RTL on the net on a site like this, by far the most common approach is to simply use a software license. So, to me, I would say that addresses all these problems by simply ignoring them. Does that even make sense to have a software license for hardware? I don't know. Some of the references point out the problems with that and therefore say there should be hardware specific licenses. And this has led to some efforts. I compile a list in the back, which to my knowledge is the most complete list of kind of, hardware attempts that I've seen. So solder pad, Tapper, these are all very different in their philosophy. When you read their rationales, they're quite different. CERN is one that I think is particularly well thought through. They offer 3 different versions, -P, -W. So this is permissive, weakly reciprocal, strongly reciprocal. They get around this bounding, whereas all the software terminology is about libraries and system libraries and dynamic linking and so on. They start from the ground up with a hardware-oriented terminology, like is a component available, and then they try to apply that both to board-level hardware and chip design. Interesting one I've never seen used. If anyone knows of a usage of this license, it's embedded within an academic paper, reference 6. A whole license embedded there. I'm unaware of any use of that in industry yet. So anyway, there are some links to licenses. Let's say it's a nascent field to start thinking about, instead of using software licensing and then guessing what the words mean, let's create new licenses specific to hardware. And then lastly, describe our approach. This is a current plan subject to change. We're building a chip. We are publishing on an outbound CERN OHLW license. Roughly, this diagram illustrates what can be done with it. The idea is, the core kind of cryptology, whatever your terminology is implemented in these blocks. There's also a RISC-V core, and then interface to some countermeasures. Countermeasures are largely physical things that you couldn't emulate in an FPGA board anyway. Therefore, we kind of meet the CERN OHLW definition here. But all you can say is there is an interface to countermeasures. So all of this will be published under that license. It will be some information that helps you instantiate it on an off-the-shelf. So you can buy a PC, you can buy an FPGA board, not too expensive. instantiate all this and run it and communicate between the PC and the FPGA board. When the chip comes, then you can run those same things and verify that, yes, the chip responds in the same way. So this is kind of the goal. So there's certain things that are exactly what's on the chip, certain things that are like what's on the chip but cannot be the same because of third-party issues. There's certain functions that are generic and we don't feel we need to emulate them precisely, and in some cases cannot be emulated precisely because they're analog functions. So that's the general approach. On inbound IP, in our case, there isn't any copyleft inbound licenses. So this kind of raises the question, is our outbound distribution actually compliant with this license? It wouldn't have to be, since we're the copyright owner. I can say that this is our goal. To us, that feels like the spirit of collaboration, even though it wouldn't be strictly legally required that our outbound match the requirements of this. This is our goal, because that feels like good faith participation in the community. Also, just a word on inspectability. We have different customer projects with different packages. One is, I would encourage you to look at this reference if you have interest in this. It's a very good long article. Bunny Huang, who unfortunately couldn't be here today, we're making this package really specifically at his request. It's a wafer level CSP. You put a redistribution layer on top of the die, bump it, and then flip, after singulation and backgrind, you flip the whole thing over and mount it on the PCB. That means the backside is basically just the raw wafer, and you can put infrared laser through that and get some imaging. He goes into why that is useful in inspecting the die. It won't inspect down to the gate level because that's like a micron wavelength, right? Infrared, and of course our process is much smaller than that. But compared to just looking at a black piece of plastic and not knowing what's inside it, it's quite a leap forward. So, in summary, even open source software is a developing field with many controversies. Board level hardware is kind of a nascent field in comparison, and then ASIC is even less mature and defined than that. Even the fundamentals are unclear, including some of the legal points and the community goals. Why do you have open source hardware? It really isn't the same as open source software. Even if the fundamentals were clear, there's complexity in implementation, especially in copyleft, given the complexity and varied artifacts in an ASIC design flow. So despite all these problems, we're trying to, let's say, carry the ball forward in as much as we can.